The live stream for today has been posted on the homepage. If y'all could go and put your name and number in, that'll count for today's attendance. Let me quickly put up an announcement with the same link for the people online, and we'll get started. Looks about right. Okay. There we go. Just a second, I want to open up a couple things in Eclipse, and then we'll get started. Last one should do it. Okay, I think that's it. Overhead is turning on. We'll go ahead and get started while that's kind of going. So yeah, thank you for coming, everyone, today. We're going to go ahead and get started. So we're going to be continuing our discussion on data structures into a new topic, kind of following the same thinking as last time. At this point, we're kind of late in the semester, so I'm not wanting to get into anything too complicated. In other words, we're not going to get into code today, like add new code, essentially. We will be talking about concepts, though, and we'll be going back to the old code that we made for the persons example, as well as the linked list for today's discussion. So if you go to the most recent module under week 16, I believe, you'll see for Monday I have posted part 5, the introduction to data structures, and that is essentially the slides we'll be covering today. Quickly download and open this up. I'm thinking about having one more short assignment, probably posted on Thursday. I'm kind of leaning towards sort of like an open-ended quiz, and you'll see what I mean about that. So a little bit more leeway than usual. More like for practice for the final test. That would be about it, I would think. I'm wanting to keep it kind of simple at this point. Since we are getting close, I know that this week people have final exams and whatnot. So I'm wanting to try to make it so that you're not having to do too much, that kind of a thing. Schedule-wise, I've already contacted the front desk and asked about the final exam schedule. As far as I've been told so far, there doesn't seem to be one yet. So I'm not sure when our final exam is specifically slated for. By chance, has anyone been told like when they're taking their final exams next week? Is anyone taking final exams next week and then like have a time specifically set up?
So, like, there's a final exam schedule. Does that help?
Yeah.
Because, like, they're like, if your class begins at, I guess, for example, this one, 4 to 4:59 on Monday, Wednesday, and then parentheses Friday. It says your class it'll have it on 3 to 4:50 on Wednesday. That's what it says.
Okay, you said what again? What time?
So if the class starts between 4 to 4:59 on a Monday, Wednesday, or Friday,
Yeah.
your exam is 3 to 4:50 on Wednesday specifically.
3 to 4:50 on Wednesday. Okay, let me open up Notepad quickly.
That's what it just says on the Office of Records and Registration for final exam schedule.
Is that 3 to 4:50 on Wednesday?
3 to 4:50 on Wednesday, yeah.
Okay. Okay. Could you possibly send me that link?
Yeah, I could do that.
Yeah, that'd be awesome if you could do that. I'm having trouble finding it, and the people up front, for some reason, don't seem to know where it is either, so that'd be great if you could send it. That sounds about right. So if there is a change to that, then I'll let you all know. At the moment, I'm assuming that's probably right. So it's usually not on the usual class time. For some reason, they really change up when the final, when you can take final exams on, final exams week. So you might want to expect to be here an hour earlier. That's pretty standard with these sort of things. So about 3 o'clock, plan to be here at about 3, I would say. Even if there is a change, it could be like maybe 3:30 or something. It's still usually earlier than when we normally meet.
That's this week?
That would be next week.
Next week.
Yeah. So,
Did you get it?
let me see. Refresh the page. Did you send it through Outlook or?
Yeah, Outlook.
Okay, I'll have to check later. I don't want to open that on the live stream, but I could probably check here. Let me just be sure. Yeah, I'll have to check in a little bit. Thank you, though.
Yeah, no problem.
Okay. Okay. So yeah, final exams, the final test, I should say. We'll actually have that next week. It'll be a lot of time, whatever it is. If something does change, then I'll let you all know. But I will post an announcement later once I'm sure I have the absolute date. So y'all will see it for sure. So that's the idea. I'll go over the actual study guide for the test on Wednesday this week. So no actual tests or anything this week. We're going to be doing that next. All right. In terms of what we're talking about today, last time we talked about linked lists. So I would like to introduce you to the next step up from linked lists, which is something called trees. We've actually sort of skimmed past the idea already. And let's kind of talk about that a little bit. Now, if you don't have this in front of you, that's fine. I didn't specify last time that you needed this. That's fine. But I have the persons example that we made a while ago, and I wanted to just kind of talk about this a little bit, as it's actually relevant for today's discussion. Originally, I used this as an example for what a linked list is, and that's still very true. So inside of main, we essentially created a list of sorts. We created Tim, Samantha, and Kelly, right? And then we linked Tim here. Let me zoom in a little bit so you can see this. There we go. To Samantha. We linked Samantha to Kelly, and then Kelly to no one. We didn't do anything for her specifically. Let me see. And so what we created is sort of like a logical list here, with Tim being the starting point, Samantha then being pointed to by Tim, and then Kelly is being pointed to by Samantha. This is a very singular linear list that we originally made. And as I mentioned, it's sort of an example of a linked list in the way that it's connected. The person class kind of acted like a node class in that it had some type of values. So we can grab, say, for example, Tim's name, age, height, and weight, or Samantha's name, age, height, and weight just by grabbing the person. And then we were able to use this to connect the different people together. We specifically looked at the mother side. And so what we have here is just a very sort of linear setup. And linked lists are very linear. You have a start point and you have an end point, and then they only point one at a time from one to the other. So going into the linked list example, when we made our nodes as the example early on, we created 3 nodes, a first, a second, third, much in the same way. Linked list does the same thing, where you'll have a node. You can then connect the node to another node, so first to second. We connected second to third. And so we had a linked list of first, second, and third. 3 nodes that kind of like connected to each other all one at a time. Again, the key here being each node is comprised of a single value and then some means of pointing to whoever is next. So it's the same kind of concept. So again, very linear. Now, if we go back to the persons example again, that would be in the person class. We had it originally so that there was both a mother and a father. We didn't really focus too much on the father's side, but it is still there and it's worth talking about. If you wanted to, you could fill out both of these variables at the same time. It would make it a bit more complex, but you could potentially do that. So as an example, let's go up to maybe like right here. Again, you don't have to do this. I just want to show you essentially the way that this would work. I could make a person called John, for example. Do the usual setup. Make John equal to a new person. Could set the age, 42 or something. Set name, I'll just keep this simple and just do these 2. John, and I think we'll just sort of like leave that there for now. So there'll be no other connections besides these 2. So we now have a John object, and we could say we originally set the mother for Tim. We could do that again here with Tim.setFather this time, and pass in now John. When we run this code, we now get a very simple thing where Tim now points to Samantha for the mother and John for the father. So what we did for Samantha, giving her a mother, we could do the same thing for John as well. We could give him a father. Either way, what we sort of have right now, I mean, we can keep going, so on and so forth. We could also give John a mother if we wanted to. Open up Paint. So this connection that we've created so far, let's do this. Increase the size a little bit, 624. So we have Tim, Samantha, and I think it was Kelly was the original one, right? And Kelly. We also now have John. Put him down here for a second. The original sort of distribution that we had was Tim pointed to Samantha. Samantha then pointed to Kelly. So again, Tim being that starting point, and at this point, Kelly would be the end. By including John into this, though, oops, move this up, we've now created the following sort of connection, where Tim now points to 2 things. Okay, good enough. There. So this is connection is a little bit different now. Tim pointed to 2 things at once, rather than just one. What we see here is more commonly called, so it is sort of like a linked list. It's the same concept. It's still nodes and everything. It's just that we've added an extra layer with sort of like a separate list at this point. And technically speaking, Tim can have, in this case, a mother and a father. But we could go even further with this, and for example, we could create a father for Samantha. Maybe name them like, I don't know, Albert or something, I don't know. Oh boy. If we did this, then we would have a connection kind of like this. Every single person can potentially have a mother and a father with this example. So Tim has a set, Samantha has a set as well, and this is kind of like, I think this makes sense, right? It's basically a genealogy at this point, starting at Tim, and then we're kind of like looking upwards towards his parents, their parents, and so on and so forth. So in Java, we have a data structure that's very similar to this. We call it a tree. It's essentially like a linked list, only instead of the node pointing to only one thing, it points to two things. So it's a slightly more complex node, and it gives us some more options in how we can organize things. And so what we see here is like a simple example of it, but hopefully it kind of illustrates what I'm getting at here. This is essentially what a tree would look like inside of Java if you were to structure it. You can still see the original linked list that we had, Tim, Samantha, and Kelly. It's just these extra little additions of John and Albert that show like the slight increase in complexity now. If we were to go back into the slides, let's kind of review here. Okay. Yeah, so for linked lists, all the data that we have is essentially stored using node objects and references to point to the other objects like we just talked about. All the elements inside of our linked list are nodes. And I think we talked about most of this already. The starting point is the head, which is also a node, and then everything sort of like starts at the beginning and then works its way to the end, roughly. This is a sort of like another example of what a linked list would look like. A very simple example. So with trees, it's the same concept, but with that added complexity I just mentioned a moment ago. There are some differences as well with the terminology. So a head is now called the root because we're looking at it as a tree. So they're saying like the starting point is the bottom of what's in a sense. So it is the root node, the very start. We also have a name for the end nodes, so the spots where the list ends. With this example here, this would be the root. I could even mention that here. And we have certain nodes that sort of like end. They're at the very, like, there are no nodes that come after them. So in the case of John, Albert, and Kelly, they don't connect to anything else. They're sort of like nodes with no connections. Nodes with no connections, we call these leaf nodes. They're basically, that means that it is the end of this specific direction that we've been going in. So John, for example, would be considered a leaf. The same for Albert. Jeez. Hold on. And Kelly. These would also be considered leaf nodes. Samantha would not be considered a leaf node because it does have connections to it. So it points to both, at least one person. In this case, Kelly and Albert, technically. Okay, popping back in. The elements inside of a tree are still called nodes. So the starting point is still technically a node. It's, the middle points, like Samantha, for example, still technically a node. The leaves are also nodes. So if you wanted to, you can still just refer to them as nodes. Those are just a couple of extra technical names that they've given to like certain special cases in the tree, the head and the leaves, essentially. The difference between a tree and a linked list really is just that the nodes in a tree are able to point to one or more elements instead of only one. So a node, well, let's keep moving. So yeah, a node can point to one element. They can point to no elements. They can also point to 2 nodes or 3 nodes or so on and so forth. It just depends on the tree and the way that you're structuring it. So you can create a tree where each node only points to, say, one element. And if you do that, then you end up with this. It looks exactly the same as the linked list from earlier, and technically speaking, that's true. If you wanted to, you could have a tree where each node only points to one element. That is then essentially just a linked list at that point. The difference is maybe just the terminology is a little different, but you can do that. So in a sense of saying, by learning linked lists, we've learned like a very simple version of what we're talking about right now, in a sense. Okay. So on this diagram, you can see there's like the lines connecting the different nodes together, right? And then we have the nodes. There are actually names for the lines, those connections between the nodes, and we have a separate name kind of like for the nodes too, representing these connections. When you're drawing out a graph like this, we often call the lines going from one box to another edges. So it's just a line that points from one box to another. And we'll sometimes call these boxes like a point, essentially. We'll call them a vertice, which I'm not going to probably mention that name too often, but it is something you'll see occasionally. If you're familiar with 3D modeling, these are pretty familiar terms, or graphing, maybe even database. This might sound somewhat familiar. The big thing is the lines are called edges. So, and then you might call the boxes vertices. Just more of a side note on that one. A parent node is a node that points to another node. So this, for example, node right here would be considered a parent. And then this node right here would be considered a child. That's the way that they normally, when you're creating a graph like this, the names they've given for them. So a child node is considered to be a descendant of the parent node. So we're moving away from the earlier examples. This is just like technically how they call these things. The root node is the parent of this node. This node here would be considered the parent of this node. The second node is a child of the root node. Third node is a child of the second, and so on and so forth. So you might hear people refer to them as that, and that's what I'm referring to. Okay? This is an example of a very generic tree where we have 3 nodes. We have a starting point, and then we have it pointing to 2 other people. A very simple example. Not too unlike something we might have done with the person's example earlier. So, if we generalize this a little bit, and this is kind of what that might look like. With trees, you kind of define how many children a node can have. So, in this case, let's see. A node might have 1 child. It could have 2 children. It's possible it can have many children. So what we have here is sort of like an example of a very simple tree where there is a root node, and then potentially it can have however many nodes you define for it. In fact, there are a number of different types of trees worth talking about. A tree with no nodes whatsoever is considered a null tree. It just doesn't have anything inside of it. Usually you'll add something to it at some point or whatever. There are 3 most common different types of actual trees that you'll create going forward. So a binary tree, we'll look at this one in the middle, is a tree whose nodes only have up to 2 children. Potentially, so with a binary tree, 1 node can have no children, it could have 1 child, or it could have 2 children. So in other words, 2 nodes that it points to, only 1 node, or no nodes. Any of those 3 options are valid. So binary. In this earlier example that we had, actually it's not in the slides, it's in the paint right here. This would be an example, at least so far, of a binary tree. So the 1 node, like Tim for example, only points to 2 nodes. Samantha only points to 2 nodes, and so on and so forth. What we have is here essentially a binary tree. Moving back in. Where was I? Right here. In a binary tree, the leftmost child, this is assuming you have 2 children, is called the left child node, and the right child is the right child node. Just simple terminology there. Now, there is also, let's see, a good way of explaining this. There are 2 other types of trees, generic trees and n-ary trees. Nary trees? I'm not really sure how you say that. Excuse me. A generic tree is where a node can have basically any children, any number of children to it. You can have 0, 1, you can have more. There's no specifically defined limit to the number of children that a tree can have. So you can have like however many that you want. An n-ary tree is very similar, the difference being that you specify a cutoff to however many children it can have. So you will have n a number as the maximum number of children that a node can have. So it can have either 0 children or n children, where n is whatever number. say you said that the n is 10, for example, then that node can only have up to 10 children. So you can have 0 children, 1 children, 2 children, or 10 children, anything in between that. That's just an example. If the n were a 2, then you basically have a binary tree at that point. You might even be able to change that number dynamically, depending on how you set up the tree. But
so is in just the variable, or so you basically set a new variable in equal to, say, whatever the user inputs. So it's basically just a variable of all it is.
Yeah, it's basically like a limit of some sort. Kind of like, think of it like a max value, like a max number of nodes you can have for children, essentially. So, yeah, a binary tree is kind of like a 2-array tree, and then this is like making up your own version, if that makes sense, yeah. That makes sense?
Yeah, I'm just thinking about how you pass the value into it. I guess if I see an initialization, like how you actually set it up, it would make sense as far as how you dynamically use it.
I guess it just sort of depends. You could get really complicated and make n an actual variable, or you could do something like we did originally with the persons example. Or let me go into the linked list example from earlier. With the linked list, we basically have like a 1-array tree, if you're looking at it like that. There is one connection that each node can have right here. If we wanted to make an array tree with a max of 3, then we could have 3 of these, like this. And so now we would have a node that can point to 3 elements, if that makes sense. If you wanted to make a tree that points to 4, you could just add another next on here and then have 4, essentially.
Okay, I see.
So that's one way you could do
I
it.
didn't know if it was like initializing like you did like an array or something like that, where you basically have like brackets and you insert.
You could potentially do that too, if you wanted to. That would be more complex. But yeah, you could make a node array of size. Will they allow you to do a variable here? I think they will. Oh, they will. Yeah, so you could potentially do that.
Okay, that helps.
Mhm.
So then you can basically set in.
Yep. And you could potentially set this I through the constructor. So that would be another way of handling it as well. I think that's probably more the typical example of what an n-array tree would look like too. Yeah, something more akin to that. I'll undo this for the moment, but yeah, it's it'll be in the recording. Okay.
So overall, the setup is very similar to linked list, but it gets complex in the dynamics of how it connects. It points to different values. It's not just one-dimensional, it can be multi-dimensional.
Right.
With how it points to different data within the program.
Right, exactly. Very similar to a linked list, just yeah, it is more complex in that it can point to more things at once than just like one node over. It could be many, potentially. Okay. How many more slides do we have? I don't think there's that many in this set. Yeah. So, kind of like with the example that I did earlier, there's multiple different generations with the persons example that I did earlier. So you have maybe the most recent generation, the earlier generation, the one before it, and so on and so forth. Notice how I've kind of like lined everything up too. So like Tim's on his own level, John and Samantha on their own, so on and so forth. When you're creating a tree, because it gets so complex, we've given names for each individual spot here. So like I'm not sure how you would exactly define this, but Tim being on his own spot, John and Samantha being on their own. We like to call these levels. So, for example, let me pull this over so I can define this a little better. That's okay. I guess I accidentally copied it somehow. We usually, let me see, define whatever is the root to be on level 0. From there, whatever comes after it, so this spot here, would be level 1. Whatever's below that would be considered level 3. And it's sort of like a way that we can keep track of where we are in this list, essentially, this tree, essentially. Not really needed for linked lists. You can do that still, though. So if you wanted to, you could even apply this to linked lists. It's just, you're only going one at a time, not as needed there. With a tree, it can help a little bit. So if we were to add someone after Albert or Kelly, then they would go on like level 4. So if we were to add a child to one of these, it's a weird way of putting it with this example. Yeah, so if we took Albert and say we gave him a parent, like we pointed him to someone, right? Then anything below Albert and Kelly would be considered a level 4, and so on and so forth. So that would be if we were pointing, say, like Albert to someone.
When level 2?
Oh, yeah, I got that wrong.
So with these levels, are these basically sets of data that you can pull at any time within the tree? Like if you want to find out everybody's grandparents' names, basically.
Sort of. So in order to get through this tree, we're going to have to search through it, kind of like how we would with a linked list. You start at the beginning of linked list, and then you go progressively through each node. But with a tree like we have here, it's a bit more complex because we have to go through everything. So if imagine John had a mother and a father, and they had a mother and father as well, and so on. We have to go through every single one of them. But you can kind of define them by how far into the tree they are. So Tim is the starting point, and so we can consider him to be like level 0, which is essentially equivalent to being the root at this point. Anyone who is below him, so like John or Samantha, you've essentially gone from Tim, you've moved down by 1, either into the first list down here, or you've gone the other direction towards where John is. Either way, you've only done one single step. So from the first node, you've taken one step in, and that's essentially what level 1 would be considered. And then from, say, we went to Samantha, if we take one more step, regardless of which direction, we've gone one more level down, if that makes sense. So it's kind of like, how many times have you called next? That would be like which level you're on. So for level 0, you haven't called any nexts yet, you're just at the head. For level 1, you called next once, if that makes sense.
I didn't know if the level was more functional to actual code itself.
It's kind of like you'll see it with while loops a lot. So kind of like how with linked list we have a while loop where we're going like your node is equal to node.next a lot. That's kind of like this essentially. We sort of do it in linked lists, in fact. Inside of our, let's see, here, linked list.java, in the while loop, when we started at head, we were essentially at level 0. That's where our starting point is. Every time that we called search is equal to search.getNext, so we moved on to the next node essentially in the list, we moved down a level. So the first time that we called search is equal to search.getNext, we moved down to level 1. And the second time it looped through, we moved down to level 2. And then once more, if we called it, we'd be in level 3 at that point.
So you could do like, if you wanted to find like what level you're on, you could do a level variable plus plus, and then basically
You could do that, yes. So you could have like an int that just counts how deep in you are, and then you could use that to see like what level you're at. That is something you can do. Yeah. In fact, for debugging purposes, that is very useful. You could even do that with a linked list. It's just that it's not quite as relevant for them because it's so linear. Here's another example. Another different type of tree. We have a single root node up at the top. This root node points to 3 nodes. A node 1, a node 2, and a node 3. All 3 of these, so these children of the root node are all on level 1 in this case. So if you were to, and then node 2 points to 2 other nodes, which would be on, in this case, level 2. So in other words, if we were to want to get to node 4 or node 5 from the root node, we would have to call a next once to get to node 2, and then we'd again have to call a next somehow to get to node like 4, for example, and so on. And worth noting as well, node 1, node 4, node 5, and node 3 are all leaf nodes. They do not point to anything else. Just a little kind of side note there. Okay. So a tree has some rules that make it a tree. And when you're creating a tree, you want to kind of keep to these rules. Otherwise, it becomes a different data structure entirely. It can actually be more complex if you do kind of like break these rules. So it's worth keeping them in mind. A tree is only a tree if there is a single path from one node to another. One path between every pair of nodes in the tree. Yeah, so in other words, like here we have the root points down to node 2. That's not the best example. Oh, what's happening? Let's go to node 2 next. Node 2 points to node 4. Node 2 points to node 5. So you can consider node 2 and node 4 here to be like a pair, in a sense. They're saying, like, in this case, there's only one path.
The root pointing to node 4, so it would become a bypassing.
Right, yeah, you wouldn't want the root node to point to node 4. That's a good point, yeah. So one node can only point to, like a node in level 0 can only point to something in level 1. That's pretty fair to say. Something in level 1 can only point to something that's in level 2. And it's worth noting, yeah, a tree with n nodes has only n minus 1 paths. That's just sort of like a rule. Let's look at this picture and just kind of talk about it. Yeah, so what I said is true. Nodes in level 0 can only point to nodes in level 1. And then level 1 can only point to level 2. If you're on one level, so for example, look at level 1. We have 3 nodes there. Nodes on the same level cannot point to each other. So node 1 cannot point to node 2. Node 2 cannot point to node 3. And there isn't like, they can't point to each other either. And generally speaking, node 1 in this case isn't pointing to node, to the root node either. It's just worth mentioning. It's pointing in a single direction as well. And yeah, you can't have level 0 pointing to level 2. When it says n minus 1 paths, basically that means in this case we have, what is that, 6 nodes? So there's in total 5 paths. So 5 edges. That rule is usually always going to be the case. I can't think of any examples where that wouldn't be. So if you add another node and we had 7, there would be 6 edges, and so on and so forth. If somehow you have 6 nodes and 6 edges, something isn't right.
Okay, I see what you're saying.
Yeah.
You have however many nodes you have, you're going to have minus 1 paths. Or
Yep.
edges, basically.
Yep.
Because you have the root that it's not, it has edges, but it's not really, it's kind of like the one example where nothing's pointing to it, at least it was.
Yep, exactly. Yeah, so, yeah, that's just more or less, this is like a general rule of thumb. If somehow you have more than that, usually it's something else. If you have, for example, I think I have an example in here. This example is not a tree. We actually call this a graph, which is a more complex version of a tree where nodes just kind of like point to wherever. And we're not going to get into that. But if for some reason this happens, then it's not a tree anymore, and you want to like fix it up, essentially.
It's like mine.
Yeah. Yeah, another example on the left, this is a tree, because again, we have 6 nodes, 5 edges. None of the nodes on the individual levels like point to each other, so level 1, they don't point to each other, level 2, 4, and 5, they don't point to each other, so on. Only level 0 points to level 1 points to level 2, and so on. And then on the right, we have essentially what is a graph, because node 5 points to node 4. So we have 6 nodes and 6 edges on the one on the right, which is not correct, essentially. I believe that's it. So in terms of what we're covering today, Let me think. Wasn't necessarily wanting to get into codes day since we're so far into this is normally I end this class off with a discussion on linked lists. We somehow have gotten a little ahead of the curve, so that's why I'm covering this today. So I kind of want to just leave it off with this for right now. Next week on Wednesday we're going to be covering the final exam. We're going to go over the study guide for it. It'll be relatively big, but it's going to cover essentially just whatever we didn't do in test 2 at this point. So anything from test 2 onwards. That's usually always the data structure discussions, and maybe I forget if we covered there's usually an extra set of slides. Maybe the reading into files bit might also be on it. I don't remember at the moment. We'll cover that on Wednesday, and potentially the last quiz I'd like to do, just a little simple something as well. And perhaps we'll do some practice, so maybe another discussion as well. I have something in mind that I think y'all might like that I'd like to do on Wednesday is sort of like to end off the semester on. We'll see how that goes. I think we'll go ahead and end off early today though. I don't really want to cover too much more, as if I cover more, it'll be on the test. So that's, yeah.
Did you get the link that I sent you? I guess if you want to cover the final before we go.
Yeah, let me go ahead and take a look. Yes, I will go ahead and end off the lecture for today. If anyone has any questions, feel free to ask. Let me...
I also sent it on Canvas now if you want to check there too.
Oh, yeah, I can do that. Let me just quickly turn off the projector so everyone can see my emails.
In what class did we start going over like creating shapes and I guess I can't say objects, but more like the building facility, programming, like say you want to build a digital clock or something like that.
Like an actual GUI, essentially.
Yeah.
Yeah, I don't know. Okay, yeah, I see it. I got the link, thanks. They used to actually have a class that was basically that. What was it called? I don't remember. I know they used to offer one. Essentially, they would teach you, what was it called? I think nowadays they use C# and they basically build out movies in Visual Studio, if I remember correctly. In that class, you would make windows, like actual window things. It's a lot of what we have taught in this class, except it's going to then have windows added to it. Maybe more like an intro class to either C# or Visual Basic. I don't know if they're still doing Visual Basic. They used to teach it that way. I think they switched to C# entirely. I don't know if it's still available though. You'd have to ask an advisor and see what the what's on the schedule. It might have been turned into an elective, so it's possible you can still take it. But there is at least one class. They might have a couple. I remember Professor Littleton at one point taught something like that. So there might be a couple options. You'd have to see with an advisor though.
And then data structures, like obviously the next step for this is data structures.
Yep.
So in that introduction, are they going to go back? I mean, do you know if they go back to the list and everything? Because I kind of screwed up my schedule and I didn't take a computational
Computational structures?
Yeah, I didn't take it, and that's a requirement for data structures.
Oops.
And everybody I talked to is like, okay, yeah, that's like the baseline of you going to get in the program and everything. So I don't have to go a full semester before I go into that.
So you said that you hadn't taken computational structures yet? Yeah, the discrete math one.
Yeah, I'm going to talk to an advisor and see if I can bypass that. Because, I mean, you guys probably know, was computational structures like, was it basics or were you going into like data structures? It seemed like more like the logic of
It's logic, so I'm currently taking it right now. Yeah.
I'm taking it. It's like not every section you go through is like super hard. I mean, some of it honestly feels back to even middle school level, but some of it is kind of like I wouldn't exactly know what to do if I didn't take it. Like when you get into things like combinations or some of the advanced graphs and matrices, you're like, huh, interesting.
Yeah. Okay. Have you guys already gotten into that stuff?
I mean, right now we're already in like matrix and
Are y'all building them or are y'all just like taught like
I'm just-
you don't actually do any coding.
Yeah.
You're just kind of writing it on paper. And stuff.
I see your question
maybe that's why they
about nodes.
It's just pure logic.
Give me just a second.
Yonahan.
Popping up the schedule here on the window so we can see it. Yes, this looks correct to me. So unless this is old,
Like the online portion is
Is
all.
this wrong?
So for.
This is what someone showed me.
this is what it would be. Oh, for us. Yeah, most of the computational structures class, a lot of like you learn logic tables, so like how and, or, and all those work. A lot of the logic there, so the ands, the ors, the exclusive ors, and all that, and how you would work that kind of logic, that shows up a lot in computational structures, but also in programming in general. I don't know.
One of the advisors told me, they're like, yeah, if you don't do well in programming too, you're not gonna understand a lot of concepts.
Yeah.
You basically, he told me, to sum it up, he was like, you don't understand like the basis of programming, you're not gonna understand, you keep getting get the structures.
You might, if you do really well in this class, be able to maybe take them together. Which is you might be able to get an exemption, just because a lot of what we cover in this class, so like we cover a lot of logical operators and all that here. A lot of what is in that class, we kind of do here in practice.
Yeah.
So you might be able to work out something with the professor if you need to, but I can't say for sure.
Yeah, I'll schedule it.
As far as I can tell, this does seem to be the schedule. So just have it up there on screen when I highlighted that. Should be it.
I know, I was wanting to take
So we
these
still
classes
show up
in
here to
because-
take the test on these computers, right?
Yes. Yeah, so just like with test 1 and 2, we'll be here and we'll take it in class. And then you just go when you're done. So what are nodes?
Even like when you get
Nodes are a
outside,
combination of two things.
graduate and everything, it's like-
A node contains value and a reference to another object, essentially. So like a node can point to another node, which contains a value and some type of a reference to another node. It's essentially a very simple object that only has two jobs, just to store something and point to another one. Kind of like how a worker, for example, one person may work at the front, where they could point you to someone who, like, I don't know, works at customer service. That person also has a job, right? Something to do. But then they can point you to somebody in a different part of the store. So like someone that straightens up things or stocks the shelves, right? They do something and then they can point you to something. That's essentially what a node can do. If that makes sense. It's a very simple example. Yeah.
What about you?
Computer science, yeah.
I'm not computer science, I have information systems, so. I'm not.
Yeah, man. I'm just letting you know about the meetings with all.
Yeah, no, I appreciate it. I still gotta take like really structures, and they're all.
Probably send the link out to the front desk and ask them if this schedule is updated or not. Because this might not be, it may be. We'll see. Okay, I think that was all the online questions. Any other questions? I could possibly expand on that a little bit too. So nodes, like I said, they contain a value and then a reference to something else. So they can hold a number, point to another. But then you make objects of these. So like, kind of like here. We made a node, gave it a value, and then had it point to someone. In the end, they do end up being objects. They're just objects that store something and then point to something. So you can kind of think of this as sort of like the blueprint for a node. This is basically showing us what it can do. And then an object, like our node first, for example, is sort of like the actual implementation of it. If you think of a node as a blueprint for a house, the object is the house itself that's been built. So a node has these structures inside of it. You can think of these kind of like the beams or what have you. So this makes up a node and what it is. And then this was our actual implementation of it. The difference is that in terms of what a node is, the linked list class sort of like creates nodes, links them together, does all that for us in the background. So that's essentially like the idea. The node class is like the blueprint for what it does. It can hold a value, point to other nodes, and then you actually make a node object, then do all that. So the first, for example, contains a value and a next. And then from there you can start like connecting them up. And that's what the linked list class does. It takes our nodes and then links them together, essentially. That is worth noting as well. Nodes are only used in the linked list class. You wouldn't ever use a node outside of it. Very, very rare that you ever need to do that. Maybe if you like make an extremely complex node, maybe for a game or something, I could see that maybe. Okay, yeah, so for those online, class is over, technically. Everyone that's here physically has already left. So, anyone else have any other questions? If not, I'll probably go ahead and shut down the stream. I will send out an email. I'll probably email the front desk with the link that I was given, and I'll see if that's updated or not, the final exam date. Looking like it's going to be next week, Wednesday at 3 o'clock. Will be when we take the final test. So y'all will have some time to study at least. I know most people in the School of Computing tend to do their exams this week. So everyone, I don't know, at one point I used to think giving the final exam this week was a good idea, but then I realized everyone gives their exam this week. So sort of, probably not. I'm doing a quiz on Thursday. It'll be a different type of quiz though, compared to what we've done prior. I'm wanting to make it a lot more open-ended. I want to get the exact rules set up, but it's going to be something where it's a lot simpler, essentially. Like I said earlier, the what I have in the syllabus for what we can do, it's more like a goal, but we're not necessarily going to get there. So we do have one more assignment. A quiz is usually, I think, like 10 points or something. So there's still, if you need to raise your score a little bit, some opportunity. And I think that with the quiz, you should be able to do that with the way I'll have it structured. Now, that being said, one last thing. There is still the matter of attendance. So I will be posting an attendance assignment, and I'll be posting scores for that here pretty soon as well. And as a side note, all other assignments have been graded at this point, by the way. Any other questions? I know there's like a 5-second delay. Did you have a question? Did you have a question?
Oh yeah, because I was going to ask you about what nodes were exactly, about, you know, if it's data or objects or
Oh, the question about the nodes?
sorry. Yeah, that was me.
That was you?
Yeah,
Okay.
that was me. I normally go up to the lab and take your class.
Oh, okay.
I normally, that's what I do. I
mean,
come in and like, I'm sorry, are you talking to me?
Oh yeah, I was gonna say, if you want me to explain it more, I can.
Well, I guess it just seems like a lot of work for something that seems so simplistic. Like
It is, yeah.
for, you know, being able just to point to another node. I guess what I'm trying to get the concept of what a node is that just speaking on memory allocation?
Like why we're doing it the way we are?
I guess. Is that what it's for, or is it like if I had a huge program, I'm pointing to different parts of the program, those are my different nodes?
There is one big reason that we use linked lists in general over like array lists.
Right.
And in terms of like what they do, they seem to do basically the exact same thing. But let me actually pull it open. I think we still have, was it stacks? We made a stack that's basically an array list, just like one with rules attached to it, right?
Right.
Let me see, that would be under workspace. Where was that? I think that was here. Let me copy, I'll probably just,
Then I'm thinking, am I really just, are we just printing out a list of things? Is that what the node is? A list of things?
the node is one part of the list. So just
part
one
of the
element
list.
in it.
Okay,
Yeah.
okay.
And then the linked list creates, like, it links a bunch of them together.
Okay.
Let me open this directory up. So documents, stacks.
And when we're doing code, it just seems like so much just to, especially to remove one.
Yeah, there's a lot to that.
It's like, man, we're doing all of this just to, just to take out whatever, but
Yeah.
I mean, can we make a node whatever we want it to be?
Well, did we not do that? I thought we did the,
That would only be
huh. Would I
the
rather-
power of it, that we can, it can be an object that we're pointing, one object pointing to another object, pointing to another object of some type, maybe like a string to,
I thought we did like a thing somewhere. Well, I don't know if we had the code for some reason. I guess maybe it's somewhere else, but I can explain it. So for array lists, in the background, they're implemented using arrays.
mhm.
So with an array list, I think it starts out with like it makes an array of like size 50 or something like
Yes,
that,
yes.
and you just start it'll start putting elements inside of it for you essentially.
Right.
Now eventually you hit, say you wanted to make an array list. Array lists technically don't have a size, so they can be as big as you want.
Right.
But in the background, they do have an array that's being used to implement it. If you decide, I want 51 elements, and you put it in the array list, it has to then take that array that you made, that it makes in the background, I should say, and it then creates a new one that's huge, so that it can fit all the new elements into it. And it just sort of like shoves them all into the new one. And that process takes a lot of work to do, because it has to essentially make a new array, take all your old elements, put them into the new one, and then it has to get rid of the old one, and so on. And so there's junk memory that comes up from that. So the old array is still there in memory. The garbage collector has to go through and get the original one,
Okay.
recollect it, and then like deal with it. And so that's like a big problem, is sort of like it's not completely, there are downsides to it because of that. Especially if you're working on an older system where memory allocation and all that, you don't have a lot of space, you don't have a lot of RAM or something. A lot of this really does boil down to, it was designed this way because we had so many limitations back in the day.
Right, so we're just talking, are we just talking to the RAM? Is that what we're doing? We're talking to it, saying, I want to extend this list bigger than what I anticipated, and it's not together. You understand what I'm saying? I know stacks, I think the info is the arrays, that stuff is all together.
Yeah, so originally it does something like this. We make new ARR, and maybe it was like size 50 or something.
Right.
This is the original one. It then has to go through, when you add too many to an array list, it creates a second one, and maybe it'll make it like 60 or something. It then has to go through and take everything from array 1 and then put it into array 2. So temporarily we have these two arrays that both exist at the same time.
Right.
And so it's like in memory it suddenly spikes for a second. It has all this extra that it has to do. Move everything over from array 1 to array 2. And then once it's done, this sits in memory for a bit until the garbage collector sees it and removes it. So
We didn't talk about that much. Is that something
we didn't really
worry
need
about?
to,
Okay.
because it's not really important for us. All we were interested in was just implementing it. Like, well, we didn't actually implement an array list. We only did stacks and queues. Some of the reason being of this complexity, I didn't want to get too far into it, just because it's kind of a bit much. If you were to use the built-in one, though, that's what's happening in the background, roughly. It gets more tactical than that, but that's like the idea.
Yeah, I think they mentioned a little bit in C. I think they talked about free. I think free was a keyword or something that got
Yeah.
rid of, freed up some memory or whatever. But right now, I'm still just trying to grasp the concept of what a node is. Is it whatever I want it to be? I may want to make a list of items, or I may have created some object classes, and I'm pointing this to this object here, but it's pointing to another object, which formulates my whole program. Is that how it works?
You can change it up if you want to.
Yeah.
So this is just an example. Let's see, just a very basic example, but you can modify this as much as you want to. Technically speaking, the person class that we made
Mhm.
is also a node class.
It's a node class. Okay.
Mhm.
Okay. Okay.
Yeah, because it's a person can now point to a person. As long as you have this, where like whatever this is can point to another of itself, or like a node can point to a node, then that would qualify as a node class. It's just that's the technical name. You can modify this as much as you want. You can have as many values as you want in. So you can have a single value. You can have hundreds of values in there. Just so long as like a node then points to another node, that constitutes a node class. If you make a person, and then a person points to a person, then that would be essentially a node.
In this example here, we're actually putting in the data.
Yep.
That's not going to happen all the time, mostly, right?
Yeah, normally no. You could if you wanted to, but you don't have to.
Whenever we put in the data, it just seems real specific. But then when we have to, for an example, in our last assignment, when we had to randomize something, then it made my Q class come up with an error because I didn't have any information in main to represent that. So I know sometimes we're not going to be actually putting the information in there. What if it's a whole bunch of information? You can't sit there and put in all of these integers or floats or whatever to do a program, a decent program.
Did you see the example that I posted for the answer for assignment 5?
Sir, I did. I printed it out, and I have that thing so marked up because you drove home some concepts for me. I got what every little piece does, but when it's time to put it all together, that's why I struggle a little bit because I don't know who comes first, who comes second, or it's kind of crazy. But individually, I can tell you anything about it. But when you have to, which is the job, when you have to put it together and make it a working program, that's what I'm working on.
Okay.
But no, that was excellent. It really helped me. I think I responded back to you and said it was beautiful because
Yeah.
nice
Good
code.
email. Yeah, thanks for that.
It's a beautiful thing.
A lot of it might come with just repetition, just using it a lot,
Yeah,
and then
yeah.
just making it a lot. That'll help.
Yeah.
In the next class over, you'll probably be making more of these again.
Yeah.
So you'll have more opportunities to like make linked lists and what have you. So
Yeah, it's definitely you have to put in the time, and you have to put in a little more time than just regular, to really be good at it. I'm an IT major, so I don't think I'm going to really have to get in it too deep like a computer science guy.
Oh,
But
yeah.
my interest in it,
Hmm.
it's been pretty strong for 10 years. I've been interested in it.
Yeah,
In
luckily.
programming, period.
Yeah. Yeah, luckily you don't have to get too deep into it if you're doing
Right.
IT. I was actually IT when I was an undergrad
Right.
as well. There are some classes here that they make compilers and everything.
Yeah.
So we compile things and Eclipse and all that. You basically make one of those. When you get down to like the memory level, it gets crazy.
I can imagine.
I've been playing around with C recently.
Yeah.
When you get down to that level and you start linking little memory blocks together and all that, it gets crazy. The kind of code that you can get into.
I like that.
It can be very fun though. Yeah.
I really did. But yes, sir. I will see you. Well, I'll be upstairs, but Wednesday.
Yep.
Okay. All
That
right.
sounds good.
Thank you.
Yep. You have a good day. Okie doke. Got about 5 more minutes left in the original class period. I see there are still about 3 people left. Do y'all have any questions? Otherwise, we'll just go ahead and shut down. I need to be getting ready for office hours coming up at 6. Okay, not seeing anything. So I will go ahead and end off here today. Y'all have a great and wonderful rest of your day, Monday and Tuesday, and I will see you all on Wednesday for our final class of the semester. Hopefully I'll have something interesting for you all. I usually like doing a little special discussion on the last day of class to kind of like bring everything together, essentially. Both programming 1 and programming 2, but we'll see. Never do quite know with that sort of thing, just because of time constraints. So yeah, I'll see y'all next time.